Hello everyone. So today onward, we are going to start another video series that is related to speed control of three-phase induction motor. So before I start, two things I need to cover. Like as you know, the rotor speed of induction motor is given by Nr is equals to Ns into 1 minus S. Correct? So to control the Nr, you have two things you can vary. Either you can vary the Ns or you can vary the slip of the induction machine. So there are two techniques will be there. If I talk about from broader sense, you can control the slip and you can control the synchronous speed of the from the supply. You can say. Uh, let's say so we have two techniques. So we have slip control techniques and we have synchronous speed control techniques. In case under sleep control, you have various methods. So first you can say it is the first one is the rotor EMF injection method. This particular method is only applicable to slip ring induction motor that we will see today, and why it is only applicable to slip ring induction motor that also we will see. And then stator supply voltage control, it is applicable both the induction motor, like either it is applicable to slip ring induction motor and it is applicable to squirrel cage induction motor. And the third one is the rotor resistance control, again it is only applicable to slip ring induction motor, or sometime we call it as a wound rotor induction motor. And the second one is the synchronous speed control. Like by varying the synchronous speed, you can control the rotor speed also. Like you can control the synchronous speed. Like as you know, the synchronous speed is nothing but ns 120f by p. So by varying the supply frequency, you can control the synchronous speed, and your rotor speed will also change, right? So under frequency control, you have two situations, like your supply voltage is fixed and you are varying the supply frequency. Another is that you are varying both the quantity, supply voltage and supply frequencies. It is the most important one that we also cover in another video. Like it is something called variable voltage, variable frequency control. Okay, this second one, so we'll cover this one too. And another is the pole changing technique. The pole changing technique is only applicable to squirrel cage induction motor. It is not applicable to slip ring induction motor because slip ring induction motor rotor construction is almost like the conductor wise, the way you have the windings and all. We have the same kind of winding structure in stator also, so they are fixed. You cannot change the pole structure and number of poles and all, so they are predefined, you can say. But in case of squirrel cage induction motor, you can vary the rotor poles and all. Okay, so this pole changing method is only applicable to squirrel cage induction motor. Okay, now let's start with the first one, the rotor EMF injection method. Okay, so as I mentioned previously, it is applicable to only wound rotor induction motor, or sometime we call it as a slip ring induction motor. Okay, slip ring induction motor, and why it is important. So to understand why it is important, I have to explain few things more. Like let's say your input power from the supply is Pin. So after having this input power, the power will go to the stator side. So there will be two losses. One is stator winding copper loss and the core loss. So after that, if you subtract those two losses, let's say P core loss and P stator copper loss, that is occurring in stator windings and all. So you will be having the air gap power. Okay, and this air gap power has two component. One is called slip power, SPG. Another is the mechanical developed power, 1 minus SPG. Okay, this SPG power, in case of squirrel cage induction motor, this is something we called as rotor copper loss, or rotor copper loss component of the air gap power. And in case of squirrel cage induction motor, this entire power will be consumed as a rotor copper loss. And if and this particular term 1 minus S into PG, this is something called mechanical developed power. Now, in case of squirrel cage induction motor, there is no way you can utilize this SPG power. But in case of slip ring induction motor, since you have the slip ring outside of the motor, you can do something such that you can utilize this SPG power. Okay, instead of wasting the entire power in the rotor's copper loss, you can utilize it. How can you utilize it? Let's see. If I draw the circuit diagram of the slip ring induction motor for the rotor circuit only. Just I'm interested in only rotor circuit. So let's say these are the rotor induced EMFs in case of three-phase slip ring induction motor. Okay, these are the rotor resistance, leakage, reactance, and all. Rotor resistance, rotor reactance. Now, this on this onwards, you have the freedom. You can either connect these 3 points. Yeah, like simply you need not even connect any other component. You can simply short circuit these two components, these three lines, and it will behave as a squirrel cage induction motor. That's it. But you can either add a resistance, or you can also inject a voltage from the external source. Okay. So let's say you wanted to inject some voltage in the rotor circuit. And this voltage supply basically will come from the inverters. Okay, yeah, so these are the voltage that you want to inject. Let's say it is EJ, and the voltage that is getting induced here something SE2 and R2 JSX2. Okay, and the frequency, one more thing, like the frequency of the EJ, what will be the frequency of the injected voltage? The frequency of the EJ must be same as a rotor frequency, because you have two source, you can say. So for the proper power flow, the frequency of the two source must be same. So this is the thing that inverter will take care. It will track the frequency, and it will inject the voltage with the same frequency as the rotor induced EMF. Okay, now it is three-phase circuit. I'm assuming it is a balanced one. Okay, so if I assume balanced circuit, so I can just analyze the entire thing by having only single phase. So we will do the analysis and all per phase only. Okay, now before I proceed, there are few more things that I need to discuss here. uh, let's say you have the rotor circuit, right? Here you have the rotor induced EMF SE2 R2 JSX2. uh, Now I want to transform this entire circuit to stator side. So I'm assuming the equal turns ratio and all. So I'm not even considering any turns ratio effect, but uh, let's say it is R2 only. And if you divide the entire equation by slip, you will get E2 R2 by S JX2, right? If you divide entire things by S, let's say this current is I2, so I2 is nothing but SE2 R2 plus JSX2. You can divide these equations by S, R2 by S plus JX2. So this equivalent circuit is now this one. Okay, now if you see the power input, let's say rotor power input is nothing but the power that is coming from the air gap. So air gap power can be written as Pg is equals to E2 I2 cos theta 2. Okay, this is the active power, you can say. And if you draw the if you want to calculate the power factor, so for power factor calculation you have to draw the impedance triangle. So let's say this is my R2, this is my X2, like this is resistance R2 by S, and this is my X2, and this is my Z2, let's say, and this is your theta 2. So if you want to calculate the theta 2, let's say cos theta 2, so R2 by S under root R2 by S square plus x2 whole square. Okay, so R2, if you simplify this equation, R2 square plus Sx2 whole square. So this is the thing that you need to remember, like R2 by this one, R2 square plus Sx2 square, then whole under root. This is the power factor cos theta 2. Okay, this is the thing that we require for the later analysis. Okay, let me add one more slide here. Okay, so what are the things that we got? Pg is equals to E2 I2 cos theta 2 and cos theta 2 R2 J Sx2, sorry, not, it will not be J. I'm just interested in magnitude, then under root. Okay, and if I just assume the stator winding resistance and leakage reactance and neglected, then the E2 will be approximately V1, that is the supply voltage, you can say. So as you know, the supply voltage and E2 can be written as root 2 pi f phi, number of turns per phase, and kW, winding factor, like you can write like this way. So it is directly proportional to you can say uh, frequency f, and you can also say it is proportional to the flux if my supply frequency is constant. Okay, so if I put this particular this thing into the equation number, let's say it is equation number 1. So from equation 1, I'll be putting phi instead of E2. Okay, so Pg will be some maybe K prime phi I2 cos theta 2. Can I write like this way? Yes, definitely I can write this way. And also one more thing that we can discuss here, we need to calculate the developed electromagnetic torque. The developed electromagnetic torque TD is nothing but PD by omega r, the rotor speed. Okay, so if you resolve the PD, TD is equals to 1 minus S PG 1 minus S omega S. So TD is nothing but PG by omega S. Now put the PG from equation number 2 into equation number 3. If you put this, you will get TD is equals to K prime phi I2 cos theta 2 by omega S. I'm assuming a supply frequency and constant, so the omega S will be constant. So I can give another constant, something K phi I2 cos theta 2. So this is the developed electromagnetic torque. So this is nothing but your electromagnetic torque, TD or TE, whatever you want to say. So this is the equation that are required for a further analysis. Let me write TE is nothing but K phi I2 cos theta 2. Here phi is the you can say strength of the rotating magnetic field. Okay, phi. Now for the rotor EMF injection method, I'm assuming one condition. I'm assuming the load torque is constant. Assuming TL is fixed. Okay, what will happen if my TL is fixed? Then your load torque is fixed, and then for the steady state condition, your generated electromagnetic torque must be equals to the load torque. Like if you recall the rotor dynamic equation of induction machine and all, so it is nothing but J d omega by dt te minus TL. Okay, when these two quantity are same, then d omega by dt, like rotor will not accelerate and all, it will operate in normal operating conditions. You can for steady state operation, these two quantity is same, so this and these are same, so it will be zero, and there will be no acceleration and deceleration like that, all those things. Okay, so I'm assuming my load torque is fixed, and I am injecting a voltage through the slip ring of slip ring induction motor. Okay, now let's see. Maybe I can write these equations on the top here. uh, J d omega by dt Te minus TL, and also the power factor cos theta 2 R2 Sx2 whole square. Okay, now I'm considering all the three phases are balanced, so I can do the analysis and all by having only one phase. This is my Se2, this is my R2 JSX2, this is my Se2, and here you have to inject the voltage through slip ring. Now, as of now, I am considering the voltage that I am injecting that are in phase opposition polarity, like in this polarity. Let's say I am injecting this voltage from an inverter through the slip ring. Okay, why it is phase opposition? From the circuit point of view, if you close, if you like, if you move around the circuits inside the circuit, you will see here the phase is minus to plus the polarity, and here once you comes here the polarity is plus to minus, so they are in the opposition phase, you can say, from the circuit point of view. But from the external observation, you can see these are the polarity of the both the sources are in the same direction. Okay, these are required for the phasor analysis. We will do the phasor analysis and all also. Okay, so these EJ and SE2 are in the phase oppositions from the circuit point of view once you travel through the circuit. Okay, now we have to do one more thing. As I assumed my load torque is constant, and at steady state TL is nothing but Te. Okay, and this is basically constant, this is fixed at a steady state. I can write K phi I2 cos phi 2, it is basically fixed, and K is constant, and let's say my phi is also constant. Okay, phi is also constant, that means the V by F ratio, is constant, then only your phi will be constant. Like, so I am not changing the supply voltage and frequency and all, so my phi will also be constant. So I2 cos theta 2 needs to be constant. So now we are going to see the phasor diagram from the equivalent circuit point of view. So okay, so for the equivalent circuit, I am just neglecting the stator resistance, stator winding resistance, and stator leakage reactance, and I am considering the stator magnetizing inductance. That is, I am representing here as the reactance XM, and this is my rotor circuit, and this one is my rotor circuit, and here AC2 is the induced voltage, per phase induced voltage in the rotor at running condition, and these are the rotor impedance R2 plus JSX2, and I2 is the rotor current. Okay, and if I summarize from the previous slide, like this condition has to be satisfied if there is a constant load torque, even if you are injecting a voltage through the slip ring, this condition has to be satisfied, I2 cos theta 2. So the phasor diagram, if you see the phasor diagram, it is almost similar to transformer only. So this phi is basically representing the rotating flux, and if you recall the phasor diagram of transformer, E2 will lag from phi by 90 degree, and this E2 is the induced voltage in the rotor circuit at standstill. Obviously, it is a per phase value, and at running condition, that E2 will reduce to SE2, and S is the less than 0. So here your E2 will come, like here SE2 will come, like in the same line, but since AC is less than 1, so AC2 will be lesser than the E2, and your rotor current will be lagging in nature. Why lagging? Because rotor circuit contain resistance and reactance, so definitely the rotor current will lag the rotor induced voltage. So this is my I2, so it is lagging by angle theta 2. So it is my rotor power factor angle. And if you do the phasor summations of the even if you apply the KVL inside of the loop, what you will get, you will get AC2 equals to I2 R2 plus I2 JSX2. Okay, this is the thing that you will get. So resistance drop will be in phase with the current. So this is in phase with the current I2 R2, and this black one, is basically I2 SX2. And if you do the phasor sum, you will get SE2. Why it is SE2? Because if you see, if I remove for this, for a clear picture, if you see this particular one, if you take common I2 R2 plus J SX2, this particular quantity is nothing but Z2. Okay, so AC2 will be same as I2 Z2. So here AC2 is nothing but I2 Z2. So you have this phasor now. And if you see the cosine component here, I have mentioned it as a red color, so I2 cos theta 2. So whatever condition whatever EMF voltage you inject, your cosine component of rotor current should be in parallel to the this red one, like this. It should be parallel to this one, I2 cos theta 2. So this is the important point that you have to keep in mind. Okay, I hope it is clear. So now let me erase these things. If you see the previous slide, here I have mentioned like I am injecting a voltage that is in phase opposition from the in circuit point of view, like it is in opposite phase, like they are in 180-degree phase, you can say. So let's say there were no current initially, so there are no EMF injections, sorry. I- if there are no EMF injection, like E is equal to 0, then what was the rotor current? That rotor current was I2 is equals to SE2 R2 plus JSX2, correct? And this is my I2. And the moment you inject a voltage EJ equals to, not equal to 0, then your I2 will be simply SE2 minus EJ by R2 plus JSX2. I should say this I2 as a I2 prime, okay, because you are injecting voltage, so you will not get same current as the previous value, so there will be change. So that's why I'm mentioning it as I2 prime. And you can see from this particular equation, your I2 will reduce, right? Your I2 prime will reduce. If I2 prime reduce, then what will happen? Your torque production will also reduce, because I2 will create a flux. Okay, this is rotor flux, and the if I2 magnitude decrease, the rotor flux production will also decrease. So the interaction torque will also decrease. So you can say there will be a reduction in the electromagnetic torque, right? Because maybe I can write in this way to explain you better. If I2 prime decrease, then the rotor flux, I'm calling it as a phi 2, let's say, it will also decrease, and the electromagnetic torque TE is proportional to phi 2 sine delta. Okay, so this phi is the stator flux and phi 2 is the rotor flux. So this electromagnetic torque TE value will also decrease. Okay, if TE value decrease, then what will happen? If you recall the rotor dynamic equation, let's here I have mentioned previously, if TE value decrease, then what will happen? Then this particular quantity is basically negative. Negative means what? Your d omega by dt is simply reducing. So your your rotor speed is reducing. If the rotor speed is reducing, then what will happen to the slip? What will happen to the slip? The slip simply it will increase, because if you recall, the slip is equal to ns minus nr by ns. So your slip will increase. Okay, let me explain you one more time. The moment you injecting a voltage EJ, this I2 current will simply reduce, okay? And this I2 current will simply change from I2 to I2 prime. And as I2 prime, there is I2 prime, definitely it is less than I2, so there will be reduction in the flux, rotor flux, and the electromagnetic torque is directly proportional to phi and phi 2. Phi is the stator flux and phi 2 is the rotor flux, and angle of between these two. So as phi 2 is decreasing, the electromagnetic torque production will also decrease. And from this particular rotor dynamic equations, uh, as TE is decreasing, so TE minus TL, this particular quantity is becoming negative. Negative means your d omega by dt is negative. That means your omega is reducing. Omega means here the rotor speed is reducing. If the rotor speed is reducing, here you can say your rotor speed is reducing slowly, so your sleep will increase. Right? Your sleep now it will change from S to S2 prime. S to S maybe S prime. Here S prime is more than S. Okay, here your S prime is more than S. Now you have injected some voltage and finally you are achieving a sleep that is more than the initial sleep. Then obviously you could able to change the motor speed at constant load torque. So we will understand like how it happened, like the transient phenomena. This is how the rotor EMF injection method actually working, and we will see few more things, like let's say from the figure point of view. Here what are the things that we have observed, like S prime is more than S. That means your speed of the induction motor is reducing. Okay, now tell me one thing, what was the cos theta 2, the rotor power factor, that was R2 square plus Sx2 whole square. If your S prime is increasing, so here let's say this was a slip x2, so this particular quantity will also increase. If the denominator increases, that means your cos theta 2 will simply reduce. If the cos theta 2 simply reduce, that means your theta 2 is simply increase, right? Your the rotor power factor angle will also increase. So that means initially you had theta 2. Now after increase, this theta 2 will become theta 2 prime. Okay. Now let's say, let me draw it. Maybe I can use this color this time. So your theta 2 will increase from theta 2 to theta prime. So here it will come. And this is your angle, and this angle is nothing but theta 2 prime. Here theta 2 prime is more than theta 2. Okay, and you can see this is your I2 prime, and the cosine component of I2 is exactly now same. It is in the same parallel line, so it will be I2 prime cos theta 2 prime. Now your rotor current has increased now, and again if you do the analysis, like if you do the phasor sum of the resistance drop and the reactance drop of the rotor circuit, you will get the same E2 and all. Okay, and let's see, this is clear, like the phi 2 prime will increase, and sorry, theta 2 prime will be more than the theta 2, and I2 also increase. So now it is clear, like let's say this was your torque slip characteristics of induction machine, and you had a constant load torque, maybe you had a constant load torque, and you made some changes, and what you have done, let's say initially this was the operating slip, maybe now you have made some changes in all, and your operating slip as here, and your graph maybe we have to analyze the graphs and all, but approximately the point graph will cross from this particular point. Maybe I can draw it more accurately. uh, so here you have the operating point now. Okay, So this is S2, sorry, S prime, and this is your S, okay? And S prime is more than S. So this is the thing that will happen. Now we will see what will happen to the EJ phasor. EJ phasor, or the phasor of the injected voltage from inverter supply and all. So the EJ is in phase opposition. So if your E2 is in this direction, there will be, that will be in phase opposition. So this will be your EJ direction in phasor. And at steady state, we have seen, like at steady state, your S prime is more than S. So your S prime E2 will be more than S E2. So maybe where I can show it, S prime E2, S prime E2, maybe here I can show it, S prime, S prime E2, and sorry, no, it is not S prime E2 actually, it may be, it will be slightly larger than this. So here let's say it is your S prime E2, because I have to subtract also, right? So if I subtract this particular EJ voltage, I'll be having this as a resultant phasor. So this phasor is representing S prime E2 minus EJ. So this phasor is representing like this. I'm moving that way, so just that the picture can be bit clear. Okay. Now I'm removing the unnecessary things. Let's say I'm removing this one. Maybe I can remove this too. Now you have this I2 prime. Once you have this I2 prime, see, this is your, this particular phasor, this blue line, this one is exactly parallel to this. I am just removing the phasor here because of picture clarity, okay? Or else this phasor will lie here only, okay? So I have just moved it to at this position just for clarity, okay? Now if you do the phasor sum of the this rotor resistance drop and rotor leakage reactance drop and all, so this is your if this is your rotor resistance drop at steady state I2R R2, then this will be your drop of I2 prime S x2. Okay, so this is how your I2 will decrease or increase, your your power factor angle will decrease or increase. So there can be several scenarios, like here you can inject a voltage which is aiding in nature, like it is in phase with the SE2. You can do several kind of operation. You can make this induced voltage angle whatever you want. So that is depends on you. And one important thing here you have to observe, like if you see this particular source EJ, here the I2 current is flowing from positive to negative, like in this direction it is flowing. So once current like flows from positive to negative across across any source and all, so that means this particular EJ source is basically consuming power. So this is the great advantage that I was mentioning previously. Instead of wasting the slip power into the rotor copper loss as the form of rotor copper loss, you can get that power and you can inject that power to your source. Like for example, if I draw equivalent circuit diagram, let's say uh, this is your induction motor. Let's say it is your induction motor, and this is your slip ring. This is your slip ring. Let's say this roughly I'm drawing it, and you have this status supply, okay? And in status supply you are injecting voltage with the help of inverters and all. So you have this, let's say you have this AC supply and DC. Let's say you have to convert the AC to DC because this AC is the sleep frequency, so you have to convert this to DC, and then again you can convert this DC to AC of the required frequency, and you can inject this power to grid, okay? And like so you are actually utilizing the power in a better way. So that is a great advantage. why to lose that power in that rotor copper loss? Better to feedback to grid. It will do some meaningful work. So uh, this was about EMF, rotor EMF injection method. Maybe I can summarize one more time. Uh, yeah. So I hope it is clear, like why it is applicable to only slip ring induction motor and why it is important, because you have you need not to even lose any rotor copper, or like there will be losses definitely, but you can recover some amount of power and you can feed that power to grid. Okay, and I hope this equation is clear. This is the rotor per phase circuit, and this is your air gap power, and this is your rotor power factor cos theta 2, and there is the equations and all. Okay, one more thing, you can also see here the E2 is the induced EMF at the rotor at standstill condition, and this E2 is constant if you are not even changing VF and all. Okay, so from this particular equation, this equation number one itself, from equation number one itself, you can also write, since E2 is constant, so PG is basically KI2 cos theta 2, like here. And from here also, if you proceed, you need not to even convert the equation into flux form, but there will be a scenario, there will be some cases where flux will also come into picture. So that's why I replaced that E2 term with this with flux. Okay, that will be another scenario in variable voltage, variable frequency, constant voltage, variable frequency, and all these cases, this equation, I need this equation in flux form. So that's why I've just changed from E2 to 5. Or else from this equation also, you can proceed and you can see that torque, electromagnetic torque, will be KI2 cos theta 2 by omega s. So Ke is equals to maybe K double prime I2 cos theta 2, like that. Here also you can see that your I2 cos theta 2 theta 2 must be constant at steady state. So from here also you can do, but I want this phi term for the later process and later methods. So this was the, I hope this is clear how we are getting, and steady state TD and TE must be same. And this was mm, the what do you say, the result from the previous slide, this one. And this is the rotor dynamic equations. This is valid for synchronous machines, synchronous motor, generator, whatever you have. Like it is, sorry, it is for motors only. Like TE should be greater than TL, then only motor will accelerate it on. So for DC motor, for synchronous motor, for induction motor and all, this particular equation is valid. Okay, and this is the rotor power factor, and here I'm injecting voltage, and I2 cos theta 2 must be constant. This is clear. I hope this too also clear. And these are the transient phenomena. You have to understand how this transient is coming and how the sleep is becoming more than the previous sleep. And once you have more sleep, then your operating speed will also decrease. Like operating speed is decreasing, right? Sleep will increase in this direction, and speed is increasing in this direction. Okay, rotary speed. So as sleep increase, your speed will decrease. Okay, and this is the phasor diagram. Your I2 cos theta 2 will be must be constant and all, and I have tried to describe how the things is happening, and eventually you can get back that power and you can feed back that power to grid. Okay, this is the thing that I wanted to discuss. If you have any doubts, you can write down your query in the chat box. Also, maybe you can try few things more, like you can change the EJ polarity, and whatever EJ you wanted to put, you can just put, and you can just try to check what is happening inside. Okay, if you face any issues and all, you can write down in the chat box. Thank you.